Hello everyone, welcome to this course. The title of the course is Machine Learning for Core Engineering Disciplines. My name is Anand Govindarajan. I am a faculty in the Department of Chemical Engineering at the Indian Institute of Science in Bangalore, and in this course you will be learning about how machine learning can be understood and deployed in various core engineering domains. So, we will begin with an introduction to data science, and as you know that a lot of data is being generated around the world, whether through simulations or through experiments or through theories, and data science is the application of statistical and mathematical principles to analyze and understand all the data that is being generated, right. And probability and statistics, they play a very major role in data science owing to the probabilistic nature of many of the physical, chemical and biological processes that occur around us, right. Because inherently there is some stochasticity associated with these processes. So, every time you do an experiment or every time you do a simulation, you get a slightly different result, right. So, and then you start talking about averages or means, you talk about the variance or the standard deviation. So, these are very common terms in probability and statistics, and they play a central role in data science. Now, artificial intelligence is like a buzzword in recent years. It has become very prominent, and it is postulated that it is going to bring about a sea of change in the way in which engineering and science are practiced all throughout the world. There is a race for various nations to become leaders in artificial intelligence, and its importance cannot be understated in the current scenario. Now, what is artificial intelligence? It involves imparting human like cognitive functions to machines so that they can make inferences and decisions based on input data, right. Now, as humans, we interact with the world around us. We gather a lot of data through our sensory inputs, whether it is through our ears, our nose, our mouth, our eyes and our skin, basically the 5 senses, and then we are constantly processing all this data and then making decisions, inferences and so on and so forth, right. So, when you teach computers how to use the input data to make inferences and decisions, that becomes the field of artificial intelligence, right. And naturally it means that given a certain situation or data, an AI that has been developed can make an informed decision and perform some action based on that. And because of this favorable characteristic, several deployments of AI are already underway. For example, in chatbots, right, you may be interacting with ChatGPT or Gemini or Microsoft Copilot. So, all of these are chatbots. And then of course, there is example of self-driving cars, speech recognition, computer vision and so on. In all these examples, the computer is processing a large amount of data and then using it to make inferences and take decisions and perform certain actions. So, that is key to AI. Now, if we come to machine learning, it is slightly different, right. So, machine learning is somewhat different from AI. It is the use of computers to learn rather than memorize data sets involving a number of variables so that they can make predictions corresponding to unseen data points, right. And therein lies the utility of machine learning, right. It may not have seen a particular data point at all, but yet it can tell you what will happen. For example, if you have a computational fluid dynamics simulation, CFD for short, which is often done in fields like chemical, mechanical, civil, aerospace engineering, to understand how liquids or gases or mixtures of them, they flow through reactors or perhaps the flow of air around an aeroplane or an automobile, right. So, these simulations are computationally very demanding. So, if you look at high performance computing clusters around the world, a lot of these simulations are running. Now, the question is, can we take the data from all these simulations and make a machine learning model which will be able to predict the outcome of those simulations without really doing all the heavy lifting, right, that is required for solving the underlying very complex non-linear partial differential equations, right. So, that is the value of machine learning, that it can work on unseen data points. And this distinction between learning and memorizing will also sort of appeal to you from a day to day manner in which we may perhaps function, right. Oftentimes we realize that if you memorize something, you may not retain it for a long period of time, but if you really learn a concept, then it sticks with you for a longer period of time. Machine learning in some sense works in a similar manner, right. If you have a very complex model that does not really learn what is happening, but rather just sort of memorized, and we will come to what it means later, then it will not generalize very well to unseen data. So, the predictive power of the model will be compromised, right. That is something we do not want to happen, and we will discuss in future lectures how we can mitigate such issues. Now, if you look at certain data set, let us say you have actual data that is coming from either simulations or from experiments, and then you have somehow made a machine learning model, right. So, you will have some predicted data. Now, you can plot the predicted data versus the actual data. These are the blue points, right. This is just some made up data in this case, and each of these points is a data point, right. Now, I have drawn in this dashed black line the y equals x curve. So, this actual data is on the x axis, the predicted data is on the y axis. So, this dashed line is the y equals x curve. So, if your model is perfect, then each point should lie exactly on the y equals x curve, but no model is perfect. So, you will see that these points often they deviate from the curve. So, if you are above this curve, for example, that means your predicted value is higher than your actual value. So, your model is over predicting a certain data point, and if a point lies in this region, then that means your actual value, right, that you measured in the experiment or got from a simulation, high fidelity simulation, that has a higher value. So, your model is actually under predicting, right, and on this line if you lie, your performance is really good, right. Now, are there ways to quantify this performance? Yes, there is something called a loss function which can be defined, there is something called goodness of fit or the R squared value. These are all metrics that are required to train machine learning models, and we will also discuss these in this particular course, right. Now, one may also think about what is the relationship between AI and ML. After all, they are sort of connected, right. It involves a machine processing data, understanding it, making inferences, decisions and so on, right. So, clearly there is some link between them, but they are not quite the same, right. Now, what I will present here is one way of looking at the relationship between AI and ML, and others may have other ways of looking at it. So, you can of course, once you learn the subject, you can formulate your own thought process and viewpoint of what exactly is the link between AI and ML, right. The way I see it, in AI there are machines which make decisions and or take actions based on those data or the decisions, right, whereas machine learning is actually a subset of AI. So, this is a Venn diagram. So, the larger circle, the all encompassing circle I have drawn to be artificial intelligence, and within this is a smaller circle, that is machine learning, right. Machine learning makes predictions or learns patterns in the underlying data, right. So, here you are only sort of confined to making predictions or understanding the data, but in AI once you have processed the data, you are also taking actions, you are doing more, right. So, in that sense that is why the Venn diagram is drawn like this, right. And now there are three very important concepts that feed into both AI and ML, and any practitioner of machine learning, whether they are from computer science or they are from core chemical engineering, civil engineering, materials engineering, mechanical engineering, aerospace engineering, biochemical engineering, all these branches, anyone who is interested in using ML should know at least a little bit of linear algebra, right, how matrices work, how do you solve a set of linear equations, right, all those are very important concepts. What are eigenvalues, eigenvectors, singular values, right, we will touch upon these concepts in this course. The other concept which is important is probability and statistics. I already alluded to in a previous slide that because the data that we collect is the result of some stochastic simulation or stochastic experiment, probability and statistics are central to the field of machine learning or statistical learning. And finally, necessarily machine learning involves a lot of data points, right, and therefore you have to understand how all the data points and all the various features of a data point contribute to the final prediction that you are trying to make, right. So you are dealing with a lot of variables, right, a lot of variables, whether you are talking about the features, right, of each data point or the number of data points itself. There is a large amount of data that is involved. So multivariable optimization or multivariate optimization will play a big role in training our machine learning models, right. So we must get familiar with the concepts of linear algebra, probability and statistics and multivariate optimization, and I will introduce these concepts as and when they are needed. In fact, going forward a few lectures I will start teaching the basics of probability and statistics because it is important to build a strong and solid foundation in this. My notation will be somewhat simplified. If you look at courses which are taught by computer scientists, they will involve a lot of rigorous mathematics and notation. I will try to simplify this notation so that core engineering disciplines, students from those disciplines and practitioners from those disciplines will find it easier to follow the material that is covered in. I will also introduce some concepts from linear algebra. They are particularly important when we talk about linear regression models, which is the simplest kind of machine learning model that one can envision. And finally, when we will talk about training of machine learning models, then we will introduce algorithms which can be used to optimize multidimensional functions. So that will also be covered in this course. So let us move on, right. I want to begin sort of with a very brief history of AI and ML. Of course, I cannot do justice to all the countless researchers and scientists who have worked in this field and who have been pioneers in this field. So I will only lay out a brief sort of timeline as to what happened, and I may certainly make omissions, so apologies for that, but you have feel free to read many other sources and try to understand what really happened over the years which led to the development of the advanced AI and ML algorithms and the state in which we are in, wherein we are almost every day interacting with artificial intelligence, whether it is through chatbots or through AI assistants like Alexa or Google Home and so on, right. So I will start somewhere in the 1950s to 1970s, and of course ML and AI algorithms, there have been developments before that, but I will start in this period because a few important things happened here. In 1950, Alan Turing proposed the famous Turing test, which is sort of a test that a computer should undergo if it has to prove that it is human like, it has human like intelligence. So that happened in 50, and going forward to 1956, a very important workshop known as the Dartmouth workshop was organized by pioneers of information theory like Claude Shannon and others like John McCarthy, Nathaniel Rochester and Marvin Minsky. They actually coined the term artificial intelligence in a proposal for this workshop, and then this workshop was held and since then it has influenced a lot of thinking of researchers in this area. And in terms of when the word machine learning first came into parlance, it was in 1959 when Arthur Samuel, he defined ML as the ability of a computer to learn without being explicitly programmed. So you will see that in machine learning we train a machine learning model, but there are no explicit instructions as to what the ML model should do to predict a given output, right. And in this sort of age in the 1950s to 70s, there was more focus on symbolic artificial intelligence. People were working on rule based reasoning, rule based problem solving and concepts of this type. So if you move forward to the next 20 or 30 years, you look at the 1980s and the 1990s. There was of course a period in between when there was sort of a mild lag, some people call it the AI winter, but in this era sort of the statistical models of machine learning rose to prominence. There was a shift from rules to data driven learning, right, and in particular there was a very important rediscovery sort of back propagation, which is a very important concept involved in the training of artificial neural networks, ANNs, right, and we learn how back propagation works in a simple manner, right, in a conceptual manner. And finally, this also led to resurgence of recurrent neural networks, right. Typical neural networks, they do not work on sequential data, the artificial neural networks, they do not work on sequential data, but what if you have a sequence, you have a time series, you have a data in which the previous sort of features influence the next set of features, which is what happens in text and so on, and these require the use of what are called RNNs, recurrent neural networks. So there was work in terms of the Hopfield networks and the long short term memory, LSTM as it is called, right. Now we will see how much time we have to delve into these concepts in the course. And finally, there was rise of other statistical methods like the decision trees, some people call them classification and regression trees, CRTs, there was support vector machines, gradient boosted decision trees and so on. There is of course a lot of acronyms, short forms involved here, but the hope is that as the course proceeds, you will be able to understand many of these terms that are being used, right. And finally, I come to the era of the 2020s, right, 2000s to 2020s, wherein there has sort of been a deep learning revolution, and deep learning refers to the use of neural network models because they consist of very many number of layers and the models are quite complex, and this was made possible due to the explosion of big data and GPU computing that has come today, right. If you look at modern high performance computing clusters, supercomputers around the world, they are embracing GPUs, and this is because GPUs are particularly suited to train AI ML models very quickly, they are very efficient and more efficient than CPU architectures, and that has played a big role in the present day world. And of course, there have been breakthroughs in computer vision, something known as ImageNet was developed, also developments in natural language processing, NLP in short, where there were concepts like gated recurrent units, transformers and attention, and these transformers basically led to the development of ChatGPT, right, which was the first sort of LLM which a lot of the public was using, and of course GPT stands for generative pre-trained transformer, and this transformer architecture plays a very important role in that, right, and we will try to sort of briefly introduce these concepts in the course. And in terms of real world applications, there are applications in medicine and healthcare trying to improve how patients interact with doctors, how they can get the best possible healthcare, early diagnosis of diseases. That is a very important area in which progress has been made, and of course like we already discussed, we can look at things like self-driving cars and virtual assistants, right. People can have their own assistants, whether it is audio assistants or text based assistants. We are probably soon looking at a day and age where we can use a chatbot to make travel bookings for us, hotels, flights and so on and so forth. And recently of course this is something that is very important, the 2024 Nobel Prize in Physics was awarded to John Hopfield and Geoffrey Hinton for their foundational work in machine learning and artificial neural networks. So that brings an end to the very brief history of AI ML that we will talk about in this course, but like I said, you are very welcome to look at other sources which document this in much more detail and also list out the roles played by many other scientists and visionaries in this field. So now a question arises, why are AI and ML gaining popularity now, right? Well, what is it that has changed, especially with respect to the core engineering disciplines, right? So something certainly has changed, which is why we are seeing sort of an emergence of other engineers than computer engineers wanting to use AI and ML tools, and that is because there is an availability of very large amount of data, right, and like I said, there is a lot of supercomputing power that has increased. This for example is a photo of the Parampravega supercomputer, which was commissioned under the National Supercomputing Mission NSM a few years ago. And all these advances in supercomputing, there are supercomputers in other institutes of the country, again through the NSM mission, and these have led to generation of large amounts of simulation data. And of course, the problem though is that these data are of variable quality, right. Now it takes a lot of time and effort to generate data. Now if you look at textual data, which led to the development of ChatGPT or Gemini, textual data is very freely available throughout the internet, right. One can just scrape the internet and get that data. The same for images. If you go to a search engine and try to search for images, you will get tons of images, right. So the availability of data is not a problem in some aspects of natural language processing or computer vision. However, when you come to core engineering and science disciplines, there is actually a lack of data, right. And also the data quality you do not know, right, because the data may have been collected with some simulation settings, but you may be interested in other scenarios, different temperature, different pressure, different flow rates, right. So oftentimes it is very difficult to get access to the data of the type and the quality you want in core engineering disciplines. So we often have to work with simpler models. So I will also focus on non sort of deep learning models, right, like the decision trees, the random forest models, right, which are often very good for tabular data of the kind we encounter in science and engineering, right. Now the other thing which has happened other than the availability of large amounts of data is the development of new and advanced algorithms to understand and predict data. And of course these advancements in most cases have been made by computer scientists, right, but we continue to benefit from the development of these algorithms because we can then use these algorithms in our domain expertise in our areas, right. And the other reason why AI ML is now popular is the ability to automate experiments and simulations, right. Earlier we were painstakingly doing experiments to collect data. Now there are robots which can automatically synthesize a material, characterize a material, as well as test its properties, whether it is battery properties or mechanical properties or interfacial properties. There are ways to automate the collection of data, and also simulations can of course be automated by intelligent scripting, and this has led to again a large amount of data. And finally, there is a rise of field specific large language models. A lot of companies want to train large language models that will help their own employees sort of quickly assimilate information and data, and therefore be able to make informed decisions, right. And this is something that has affected the popularity of AI and ML tools. Now of course with any sort of new approach, there are going to be advantages as well as disadvantages. So a discussion will not be complete without looking into the pros and cons of machine learning. Now one very big advantage is that machine learning mitigates challenges associated with a lack of closed form expressions or theories, right. So many times as engineers we are able to write down equations, for example the Navier-Stokes equations in fluid mechanics or Maxwell's equations of electromagnetism or other sorts of equations that may be applicable to your system, right. However, sometimes it's either not possible to solve those equations, they are very complex, or maybe in some fields the equations do not even exist, right. So what ML does is it allows you to defocus from the equations, right. You just look at the data and then you try to fit a model that will allow you to relate the input to the output without worrying too much about what is happening inside. So that is an advantage of ML. It is actually also a disadvantage, and we will come to that on the next slide, right. ML helps demystify data sets with a high degree of dimensionality, right. Typically as a human we are okay to work with a few sets of variables, right. However, when the number of variables reaches the hundreds or the thousands, it is extremely difficult for a human mind to comprehend what exactly is the effect of one variable on the output. So in such a scenario, when there are a large number of independent variables where each one's effect is unclear, machine learning can play a very important role in dimensionality reduction, in sort of weeding out the unimportant variables and helping us understand what are the important relationships in the data. And finally, once a model is trained, right, it can make predictions at a fraction of the computational cost. If your simulation needs 2 or 3 days to run, the ML model can probably make predictions in milliseconds or seconds, right. So, that is the advantage of these machine learning models. You save a lot of computing power once they are trained, and therefore, you can use it for combinatorial optimization. You can find the best operating condition or the best material for the application at hand, whether it is for designing batteries or it is for designing electrolyzers for green hydrogen production or the optimization of a chemical plant and so on. And I will try to list a few examples in the next few slides. Right, and like I said, there are some disadvantages of ML too, and like I already alluded to, these models require a large amount of data to train, which may not always be available or may be of poor quality. So, then if your data is of poor quality, then the predictions will also not be that great. So, that is a big problem. However, recently this challenge has been mitigated by the introduction of foundation models, so called models which have been trained on millions or billions of data points, and these models can be fine tuned based on smaller data sets, right. So, this has sort of mitigated the problem of the requirement of very large amount of data, and we will probably discuss a little bit of that in this course. The other problem, which also I mentioned, is that it defocuses, right, you from the understanding, the physics, chemistry or biology, right, in some cases, since all the focus is on data. However, there is also physics informed or physics inspired ML, which has become popular recently. There is also something known as feature importance analysis, right. You can try to find out what are the important features in your data, right, and that is possible with ML, and this also brings back the focus on what are the important features or variables in your model. So, there are disadvantages of ML, but as research goes on in these areas, there are ways in which these cons can be mitigated, right. Now, I would like to highlight a few examples of machine learning applied to engineering problems. Right now, of course, I am a chemical engineer, so I am not entirely familiar with other branches of engineering. So, these are just some starting points, but I am sure those of you who are watching these videos, you are experts in your own domains, whether it is civil, mechanical, electronics, electrical, biological engineering, and you will be able to come up with much better use cases, right. These are just some that came to my mind. For example, a chemical engineer may be interested in the optimization of operating conditions of a chemical plant to increase process efficiency. How do we increase the yield of the chemical, the selectivity of the chemical, by just tuning the operating conditions and therefore make more profits for the company. A materials engineer may be interested in the discovery of new catalyst materials for green hydrogen production or new electrodes for batteries, right, which are very important with vehicles, electronic vehicles. An electrical engineer may be interested in using machine learning for circuit design, so as to reduce the power consumption in processes, so that they generate less heat and less cooling requirements are needed. And a civil engineer may be interested in optimizing the structural layout of skyscrapers for earthquake resistance. As we know, earthquakes are natural calamities, and we want to build structures that are resistant to these kind of calamities. And finally, a mechanical or aerospace engineer may be interested in the optimal design of an automobile or an aeroplane for increased fuel efficiency, right. So, these are just some of the examples that I have listed below, and you, being domain experts, I am sure will be able to identify many more such use cases of ML in your domain areas, right. And finally, I would like to list the learning outcomes of this course before I end this lecture. What I want everyone to be able to do is to understand and deploy machine learning for various applications, and whether you are a student or a practitioner, right, of all the core engineering disciplines, you should be able to know a little bit of the mathematics that goes behind these algorithms, and then you should be able to deploy these models, right, in your own domain areas, in your domain expertise. So, that for me is the learning outcome of this course, and as part of it we will teach a little bit of Python programming, we will teach how to implement these machine learning models in Python and how to train them, how to test them, how to make sure they are working well, and then how to use them to make predictions for data that the models may not have seen, and that is where the real utility of the model will come out. In terms of textbooks, these are some of the well known textbooks in the area of machine learning. The first one by Trevor Hasty, Robert Tibshirani and Jeremy Friedman, it is called The Elements of Statistical Learning, Data Mining, Inference and Prediction. There is also an older book by Chris Bishop on pattern recognition and machine learning, though this is a bit more mathematical. And then there is also the book by Ian Goodfellow, Yoshua Bengio and Aaron Corville, which is more focused on deep learning and neural networks, right. So these are some of the reference books. Of course, you can rely on the video lectures, but if you want to really go deep into the subject, I highly recommend that you try reading some of these books in a lot of depth. It will give you a lot of confidence and it will really help you in your journey with machine learning. Thank you very much, and I look forward to seeing you in the next lecture.